So we're going to review curve sketching, which is really in our whole differential calculus unit we've done in this first term. This is going to be kind of our crowning achievement. Given an arbitrary graph or an arbitrary function that we know how to take the derivative of, we are going to see how to sketch it. And what are the things you would look for when sketching a function? Well, here are 6 things you can think of, and each one really contains more than one item. First of all, x and y intercepts. You've known how to do these for a very long time. For x-intercepts, you set y to 0. For y-intercepts, you set x to 0, and then you simplify. Vertical asymptotes occur when the denominator is 0 in a rational function. So you set the denominator equal to 0 and solve. Horizontal asymptotes. Really, horizontal asymptotes are limits as x goes to infinity of our function and as x goes to negative infinity as our function. Remember, basically horizontal asymptotes are like asking what would happen if we have a horizontal asymptote. What happens as x goes to positive infinity? Or what happens as x goes to negative infinity? Does it get really, really close to some value? So those are how we get horizontal asymptotes. Really, we just take limits. Domain and range. If you know your asymptotes, you might have an idea about the domain for sure for vertical asymptotes. Range, really, you can think about what are valid outputs. Let's leave that one for now. Local max and min and intervals of increase and decrease we get from the first derivative. And points of inflection, intervals of concavity, we get from the second derivative. If you know all of these items, you will sketch a pretty accurate representation of your function. Now for x-intercepts, this is kind of beyond us to be able to get the x-intercept of this cubic function. We can't factor it in any obvious way. So I'm just going to tell you for this question. I would tell you this on a test question or give you one you could actually solve. The x-intercept, negative 1.104. Y-intercept is easy, as usual. It's f of 0, which is 5. So we have the x and y-intercept. Let's check off this list. This is a polynomial. So you may or may not remember that polynomials have no asymptotes, vertical or horizontal. Their limits to infinity are always plus or minus infinity. And you can plug in any real number for x and get a y value. So there's no vertical asymptote. Domain and range, that we will save until we've actually done the graph. Local maximum and intervals of increase, decrease. So we're going to need the first and second derivatives for that. F of x is 3x squared minus 6x, and f double prime of x is 6x minus 6. Now, let's look at where our first derivative is 0 to get the critical points. If f prime of x is equal to 0, well, actually that means that 3x squared minus 6x equals 0. I can factor out a common factor of 3x, so x could be 0 or 2. So I have 2 critical points. And let's look. This is a sign diagram for our first derivative. So if we plug in 1, we get 3 times 1 times 1 minus 2, as we get a negative number. And this is a quadratic that opens up. So it's negative between its 2 x-intercepts, and it should be positive outside. So our sign diagram for our first derivative should look like this. So what do we know from the first derivative? Well, we know that 0, and what's f of 0? 5. 0, 5 is a local max because its tangent lines go from positive to negative slope. And we know that 2, and let's see, f of 2 is 8 minus 12, negative 4 plus 5 is 1. 2, 1 is a local minimum. because its slopes go from negative to positive. Furthermore, we also know that the intervals of this function is increasing on the intervals negative infinity to 0, and also from 2 to infinity, and it's decreasing where it's decreasing between the two intercepts of its derivative, so it's decreasing between 0 and 2. So that's what the first derivative tells us. It tells us where it's increasing, where it's decreasing, and what are its local maxes and mins. Okay, so let's look at the second derivative. What does that tell us? Well, possible inflection points occur when the second derivative, f double prime of x, is 0, which is 6x minus 6, which means x is 1. So x being 1 is where a possible inflection point occurs. And in order to tell, we need to analyze the second derivative. This is the second derivative on either side of 1. So plugging in a negative value, or a 0 even, into our second derivative does give us a negative number. And plugging in a positive value, any positive value bigger than 1, that is, will give you a positive number. So 1 is an inflection point. An inflection point occurs when x is 1. And to the left of 1, so when x is greater than 1, we have that our function is concave down, it opens down. And when x is greater than 1, it opens up, it's concave up. Okay, so let's, and then we should also say, that 1, and what is f of 1? So f of 1 would be 1 minus 3 is negative 3. So 1, 3 is an inflection point. Okay, so let's graph this. We've done local max and min, inflection points. So let's graph this. So let's plot the easy stuff first. Y-intercept is at 0, 5. Let's call this point 0, 5. We have a local max at 0, 5. So it's going to be a max. 2, 1, somewhere over here, let's say. That's a local min, so it's going to kind of open up there. And we have an inflection point at, I believe it's 3, 2. Let's see. Or sorry, 1, 3. So 1, 3 is our inflection point, and it's decreasing everywhere between 0 and 2. So that means it has to kind of, it's opening down up until 1, and then it switches and it's opening up. So you can kind of see at 1, 3, right in this range, it switches from being part of a frowning face to part of a smiley face, opening down to opening up. Now what happens left of 0, 5? Well, it's a max, and we look at our first derivative. Everywhere left of 0, it has to be increasing. So it's got to be doing just something like this. It's opening up forever, or sorry, opening down everywhere left of 1. So it's opening down here. Sorry, I had disappearing ink on there. Let me just redraw it. Something like this. And then to the right of 1, it's opening up, and it increases everywhere to the right of 2 from our first derivative. So it increases. So this is what our function will kind of look like. And this is a pretty typical cubic looking function. We kind of expected this result. But it's very nice that we can say exactly where it changes concavity, where it's increasing, where it's decreasing. We found the maxes and mins. Okay, let's take a look at another example. I'm going to need some more space. Give myself lots of room. And we're going to want to do all the same stuff as before. So let's look at, let's do let's do x-intercepts. X-intercepts, we set y equal to 0. And this in particular, if I multiply both sides by x, let's see, so 3x squared would be negative 12. X squared is negative 4, and this has no solutions. X squared is never negative 4. I can't square root a negative number, so there are no x-intercepts. Okay, what about y-intercepts? Well, y-intercepts, we just say x is 0 now. 0 plus 12 over 0. So there are no y-intercepts because I can't divide by 0. It's undefined. So there's no y-intercepts, and that's not surprising because we can recognize we are going to have a vertical asymptote when x is 0. So of course nothing can be located on the y-axis in our function. All right, so no x, no y-intercept. What about, let's do B, vertical asymptotes. You know what, I'm just going to kind of box off all these separate pieces of information. Vertical asymptotes, well, that will occur when the denominator is 0. So let's set the denominator equal to 0. The denominator is just x. So when x equals 0, we have a vertical asymptote. What about horizontal asymptotes? Now remember, horizontal asymptotes are the limits x goes to infinity of our function, as well as negative infinity. 3x squared plus 12 over x. So this limit is actually infinite because the degree on the top is bigger than the degree on the bottom. So this is going to grow forever as x grows. Similarly, as x goes to negative infinity, we are also now going to get negative infinity because it'll still go to infinity because the degree of the top is still bigger than the bottom. But we are going to have, if we plug in negative numbers for x, we're going to get positive on the top, negative on the bottom. So we're going to get negative infinity. So moral of the story, we know how the function behaves at its endpoints. And also we realize there are no horizontal asymptotes because we don't approach a finite number as we go far right and far left on our graph. Okay, no horizontal asymptotes. Now let's look at what the first derivative tells us. It will tell us where the function is increasing, where it's decreasing, and it can tell us local maximums and minimums. All right, so let's see, f prime of x. Now note, let's simplify f a little bit. Of course, f is a quotient, so if you wanted to, you could use the quotient rule. But why don't we make life a little easier on ourselves? Split up the fraction. Then we just get 3x plus 12 x to negative 1. Using the power rule, its derivative is 3 minus 12 x to negative 2. Now, where is that equal to 0? It's equal to 0 when 12 over x squared equals 3, or x squared equals 4, so x is plus or minus 2. There are two critical points in this function, and these points are possibly going to be maxima or minima. So let's take a look. This is our sign diagram for our first derivative, 2, and remember, it is very important to check also what can occur as you go across an asymptote. Sometimes functions can switch increasing to decreasing as you go across an asymptote. For instance, you might imagine something like, I don't know, say you have an asymptote. It could be increasing, right? Then it could be increasing on either side, or, and this has no maxima or minima, or maybe it's increasing and it's decreasing, right? So its behavior can change as you cross a vertical asymptote without having any critical points. So we have to respect the fact that when we test the first derivative, it could change on either side of our vertical asymptote, which is x equals 0. Okay, so let's see, into f prime over here. If we were to plug in, actually let's use this version, it's a little bit nicer. If we were to plug in 1, we would get 3 minus 12, which is negative 9. So we would get negative. We would get the same answer if we plugged in negative 1. It's negative 1 squared. Oops, stupid ink. There we go, 2 negatives. And what if we plugged in 3? Well, 12 divided by 3 squared is 12 over 9, which is less than 3. So we're actually going to get positives, positives. Okay, so what does that tell us? Well, it tells us, first of all, that negative 2, and what is f of negative 2? Negative 2 and negative 12, which is what I get when I plug in negative 2 to the original function. This is a local, change positive negative, so it's a local max. And if I plug in positive 2 and I get positive 12, there it changes from negative to positive, so that must be a local minimum. We can do our increasing and decreasing intervals. So it is increasing in 2 intervals, from negative infinity to negative 2, and from 2 to infinity. And it's actually decreasing in 2 different intervals as well. You'd be tempted to say it's increasing from negative 2 to 2. That's not actually true, because at 0 itself, it's not actually increasing or decreasing. It's just doing neither. It's staying flat. So you have to break this up into 2 intervals. Negative 2 is less than x is less than 0, and 0 less than x less than 2. So we've learned everything we need from the first derivative. It has 2 extrema, 2 max and mins, 1 max, 1 min, and it has 4 intervals where we can describe whether it's increasing or decreasing. So that's great. Let's do the second. This is all the stuff we can get from the first derivative in this box here. So you can see these questions are quite a bit of work. Let's do now the second derivative. All right, so f prime of x, if we recall, is 3 minus 12x to the negative 2. And so its derivative, the second derivative, is 24x to the negative 3, which is 24 over x cubed. Now, that is equal to 0. Never. There's nothing I can plug in for x to divide by 24 and get 0. Or sorry, divide 24 by x cubed and get 0. So there's no one point where the concavity changes. But as we've seen, if you look at something like this graph, which is kind of like a 1 over x, it is opening up left of the vertical asymptote, and it is opening down right of the vertical asymptote. So its concavity does change in this situation when you cross the vertical asymptote. Of course, if you look at one of these, which is like a 1 over x squared, it doesn't change. It's opening up on both sides. So we need to check, even though we have no inflection point, we do need to check on either side of 0 to see if our concavity changes. So if I plug in a negative number into f double prime, I would get a negative number. And if I were to plug in a positive, I would get a positive. So indeed, it is concave down left of the vertical asymptote, and it's concave up to the right of it. Whew. Okay, so I think we are ready to sketch our graph. So let's sketch. So I'll draw some axes. We have no x-intercept, we have no y-intercept. We know we have a vertical asymptote, and x equals 0, and we have no horizontal asymptote. So let's plot our maxima and minima. So maximum is -2, -12. And the minimum is at 2, 12. These are local maxes and mins. And let's see. So we know it's concave down. It opens down everywhere left, and it switches from increasing to decreasing across -2. And we know it's concave up on the right, so it switches from it's opening up, and it switches from decreasing to increasing at our max and our mins. And now if you check this on Desmos, you'll actually see it kind of goes up like this, and then actually kind of forms a pretty straight looking line, which we don't really know enough to do that, so I would have sketched it as originally drawn. So this is a sketch of our graph. It's a pretty cool graph that we definitely could not have done before. So give the homework a try in your workbook. Can't remember where I put it. Yeah, page 126. The only way to get good at these is to do a lot of them.